So now we're ready to construct the quadratic residue block design. So let's just recall what we had in the previous video. So P is 4n plus 3 is going to be a prime number. And then we defined, Q is a certain subset of Z mod P. And the size of Q was going to be 2n plus 1. Q is this set of quadratic residues, and one of the theorems we proved is that that has size 2n plus 1. And then dx we had these sets dx, so for every non-zero element of Z mod P. So the definition was that dx is a set of pairs uv in q cross q with u minus v equal to x. And we proved that the size of this set dx is n for all x. Okay? So these are the ingredients that we need. Okay? So we're going to define a matching problem. Which we're going to hope to prove is a block design. So your set V and B are both just equal to Z mod P. And so we kind of think of it, if we represent this as a board with some squares blocked and some squares unblocked, and so square I comma j is unblocked if and only if I minus j is a quadratic residue. Okay, so what are our column sets and row sets then? So Cj is the column set, so that's the set of pairs. So that's a set of elements I such that the square ij is unblocked. In other words, that I minus j lies in Q. Or another way to say that, this is just the same as the set j plus Q. And similarly, the row set Ri, so that's the set of j for which the square I comma j is unblocked. So that's the set of j for which I minus j is in Q. Or in other words, the set of such a set of j such that I minus j equals Q. Some Q in Q. Okay, but then so this means that this can be rearranged as j equals q as I minus q. So this is just the same thing as I minus q. Okay. So what do we see here? Well, it's kind of clear. Well, firstly that the number of varieties and the number of blocks, these are both equal to the size of the set Z mod P. In other words, that's P, which is 4n plus 3. And the column sets and the row sets, from this it's clear that these both have the size of these is just the same as the size of the set Q, which was 2n plus 1. Okay, and that's most of what we need for a block design. The only extra thing that we haven't checked so far is about the intersections of the rows. Okay, remember the last condition for a block design is that if you take a intersection of any two of these R sets, the size of that should be this constant lambda. And so what we're going to prove is that intersection of any of the two of these Ri's has size n, in fact, so that this is going to be a block design with lambda equal to n. Okay, so here's the claim. If I is different from j, then there is a bijection from the set di minus j to ri intersect rj, and therefore the size of ri intersect rj is the same as the size of di minus j, and as we mentioned, in the previous video, we proved that those set di minus j has size n, and a bijection which we'll call f. And let's just recall the definitions here. Okay, so this is the set of pairs uv in q cross q, with u minus v equal to I minus j, whereas this one, ri was I minus q intersect j minus q. Okay, so how do we do this? Given a pair uv and di minus j, well, as by this, just by the definition, u minus v is I minus j, and we can rearrange that as I minus u equals j minus v. So we look at this number, well, because it can be expressed as I minus u, that means that it lies in I minus q, right? Because remember here, u and v were both elements of q. So this I minus u is an element of I minus q, which is ri, and this element j minus v is an element of j minus q, which is rj, and because these elements are the same, they lie in this intersection. Okay, so we just define f of uv to be this number. Okay, and so that lies in ri intersect rj. So that we've at least got a function like this in the opposite direction. Okay, so suppose we start with k is in ri intersect rj, which is I minus q intersect j minus q. So that means that k is going to be equal to I minus u for some u. And also k is equal to j minus v for some v and q, right? That's because k is it's an element of this j minus q, so it's like that. So now we see that I minus u is equal to j minus v, and then we can just rearrange this as say u minus v is I minus j. Therefore, the pair uv lies in di minus j. And this k is equal to f of uv. Okay, so this is showing us that this f is surjective, and it's clear from what we said here is clearly the only element with f of uv equals k, so that's proving that we've actually got a bijection. Okay, okay, so now we've shown this. Okay, so now we just need to wrap things up a little bit. Okay, so to review where we've got to, the set V is Z mod P as the size of this set, which is conventionally denoted by little v, so that's equal to P which is 4n plus 3. And then the set B, or B was also Z not P. And the size of the set capital B is conventionally denoted by little b. That's also equal to P, which is 4n plus 3. And then thirdly, each set Ri, which was I minus Q, size of Ri is the size of Q, which is 2n plus 1. And then similarly, the column sets, Cj is j plus q. Okay, and this, remember, this was denoted by R. And then the size of the column sets, common size of the column set. Okay, so K is the size of all the column sets. That's also 2n plus 1. And then we said that each intersection Ri will intersect Rj with I different from j, of course. We showed that that has the size of that is n, and so that's going to be our lambda. So that proves we have a block design the parameters conventionally listed as VB RK lambda is 4n plus 3, 4n plus 3, 2n plus 1, 2n plus 1, n. Okay, so this is an example where we've used some kind of somewhat non-trivial ideas from number theory to produce a combinatorial object called the quadratic residue block design.